For section 2 of chapter 7, we will continue our discussion on confidence intervals, but we're going to construct a confidence interval for the mean when we do not know the population standard deviation. So two things we look at. First, if sigma is not known, then it has to be estimated, and of course we can estimate it by S, which is the sample standard deviation. And then two, the same condition applies that we talked about previously, that the sample on which we're basing the confidence interval on has to be a simple random sample, and the population from which the sample comes from should either be normally distributed or the sample size should be large enough, meaning 30 or more, so we can assume that it's normally distributed. Now, this isn't something that you have to necessarily check for, but it is something you want to kind of just keep in your mind. This is a process that someone who is collecting data for a statistical study would be looking at if they were constructing a confidence interval for a population mean. Now, what I want to do is go over how to find the a t-score value, which is very similar to the z-score that we talked about previously. And the purpose of this value is so that we can look at the new formula that we have, which you'll see with this formula is very similar to the formula from section 1 of chapter 7. So we still have a point estimate for the mean, which we're using the sample mean to estimate that value. We still have a critical value, but that critical value is now based on a different distribution because we do not know the population standard deviation. And then here, our standard error of the point estimate, we use, instead of sigma, we use S. So essentially, our confidence interval formula is nearly identical, with the difference is our critical value comes from a different table, which is table F, and then instead of us using sigma, because we no longer give that information, we have to find it from the sample. So now if we have sample data, not only do we have to calculate the average like we did previously, but we also have to calculate the standard deviation of that sample. So these two concepts come from a previous unit back in chapter 3. So that was unit 2. So let me backtrack and talk about how we actually find this critical value, which is a similar process to how we found the critical value for a confidence interval about a mean when we actually knew sigma. So for us to find the critical value for a t-interval, we have to use a different table, and that is table F. Notice the confidence intervals are more or less the same, 99%, 90%, and 95%. However, how we find the critical value will be a little different. So let's, for a moment, look at table F. So here's table F for the t distribution, and table F is actually used for chapter 7 and chapter 8. For chapter 7, we only really need it for the confidence interval part, and then for chapter 8, for hypothesis testing, we'll use it for one-tail and two-tail. Notice on the table, you don't see, like you did with table E, which had a column for the z-score, these values within the table are the critical values, or like the z-score. So these are more or less like a t-score. And then degrees of freedom, well, these values are tied to the sample size. A degree of freedom just allows for variation. So if we go back to the problem, that I want to find a critical value when the sample size is 18 for a 99% confidence interval. So how we do this is, first, we look at, well, we need to find our degree of freedom, and a degree of freedom is just the sample size minus 1. So in this case, our degree of freedom would be 17. This means that because we're estimating one of the values, we are allowing that one value to be fixed, and then we're allowing the other 17 values to vary. So because we're estimating here at least one value, we're allowing that value to be fixed, and then the other values, we're allowing those to vary or fluctuate. Now, the 99% confidence interval, the concept we talked about before, is still the same. I know that the value of alpha is still going to be 1 minus 0.99, so that's 0.01, which means 1% of the area is left in the tails. So we have that t of alpha divided by 2, more or less still the same, but how we get this value is going to be a little different using the t distribution or table F. To find the value, we simply need to find our degree of freedom on this side. So in this case, our degree of freedom was 17. So degree of freedom 17. And then we need to be able to go over and find our confidence interval of 99%. So degree of freedom 17, 99%. So that means my critical value is 2.898 for this particular example. So that would be my critical value. And when I would construct the confidence interval, I would use this value. Now, the t-distribution or table F, the t-distribution has the same properties as the F distribution, or for table E, for the standard normal distributions. They have nearly identical properties. It's still a bell curve. It's still centered at the mean. They have subtle differences, but more or less they have the same properties. So when we find this critical value, it essentially is representing the same thing as the critical value did from table E. So we'll look at two more examples, and then we'll look at an actual problem on how we can construct a confidence interval about a mean when we do not know the standard deviation of the population. So I want to find the critical value when the sample size is 20 for a 90% confidence interval. So that means I need to get my degree of freedom. My degree of freedom is 19, 20 minus 1, and alpha is 0.10. So the t-score for 0.10 divided by 2, I'm going to go to the table here. So 19, and in fact, I'll scroll. So we have a degree of freedom of 19. And then I'm going to find a confidence interval of 90. So 90 is here in the second column. Find out where they meet. So my critical value would be 1.729. So that would be our critical value, 1.729. And then for the last example, I want to find a critical value for a sample size of 10 and a 95% confidence interval. So my degree of freedom would be 9, 10 minus 1. My alpha would be 1 minus 0.95, which is 0.05. So a critical value for 0.05 divided by 2. And if I go back to the table, so I have 9 degrees of freedom, and I want to go over to 95. So 2.262. And that will be my critical value. So this is how we find a critical value, which represents the same critical value from section 1, just we're using a different distribution because we no longer know the standard deviation of the population. And this information I already shown you. This is our formula. We have our point estimate, which is the value being used to estimate the parameter, which is the population average. And we have our margin of error, which is comprised of the critical value times the standard error of the point estimate. I need to fix that. It should be of. And so that's our sample standard deviation. And we'll be able to review how we find that number given sample data. All right, so let's look at this example and see how similar and how different it might be from section 1. Overtime hours worked. A random sample of 15 registered nurses in a large hospital showed that they worked on average 44.2 hours per week. The standard deviation of the sample was 2.6. Estimate the mean population with 90% confidence. So in the previous section, we went through and identified all the information that was important. So we know that we need the sample size. So sample size is 15. Sample mean is 44.2 hours per week. Sample standard deviation. Now this is different because before we were given the population standard deviation. Now we're given the sample standard deviation. So that changes things up as far as the formula we use and the table we use. And we want to estimate the mean population, in this case the mean number of hours worked for all nurses in this hospital with 90% confidence. So 90% confidence, that means because we're using a different distribution that requires us to find degrees of freedom, we had to go find those. So 14 degrees of freedom. And we want to go to our table. using the 14 degrees of freedom and the 90% confidence interval. So when we go to our table, we look for 14 degrees of freedom and 90% confidence interval. And so our critical value is 1.761. That'll be the value that we use to help construct our confidence interval. Now our formula looks very similar to before, right? We have a point estimate plus or minus the margin of error, no difference. The only difference, that part is no different. However, the difference is that we're using a different table to find our critical value, and we are using a sample standard deviation. In this case, we didn't have to find it calculation ourselves, but in the next two examples, we will review how we can find that value by calculating it like we did back in chapter 3. So we set this up, 44.2 plus or minus critical value and the standard error of the point estimate. And so this is our margin of error. So on average, for those 15 registered nurses, they averaged 44.2 hours in a work week, and the confidence interval is allowing that to vary by 1.182 hours. So this is more or less what we're subtracting from the hours they worked and also adding to the hours they worked to create that interval that is estimating the true mean number of hours for all the nurses in this particular hospital. So when we get our confidence interval, we have 43.02 to 45.38 hours per week for all nurses in this particular hospital. Then we write our little statement like we did last time. So we are 90% confident the true mean number of hours for all nurses, for all registered nurses in this hospital, and it's only in this hospital and not all hospitals because the sample only came from one hospital. So we can really only generalize this to all the nurses in this particular hospital. Had the sample come from various hospitals in a region, then it would be all nurses in that region. Had the sample come from a sample of nurses from the entire country, then we could generalize to the country. But because the sample only came from this hospital, then we can only generalize to this particular hospital. Because I mean, I'm pretty sure there's nurses that, if this is containing 90% of hours that nurses worked, I'm quite sure there's nurses that work far, far more than 44 hours. Probably not too many that work less than 43 hours, but probably a lot that work more than 44 hours if we kind of think outside of this hospital. So maybe just the location is just not that busy compared to maybe other regions, just as a large hospital. So where was I at? Oh, sorry, got off track. So we are 90% confident that the true mean number of hours worked for all registered nurses in a large hospital is between 43.02 and 45.38 hours. I didn't say hours again because I said hours up here. So those two values are pertaining to hours. And depending on your homework, how it asks you to round, this says the nearest whole number. So between 43 and 45 hours. But that, again, is our 90% confidence interval. So it's taking the distribution of hours worked for every nurse in this particular hospital, and we are looking at the middle 90%, and those are kind of the boundaries. So anyone that has between this 43 hours and a little over 45 hours would represent 90% of the population of the nurses if we look at the distribution that way. So we're capturing about 90% of that data, and so that's why we're 90% confident that the true average, if we did have access to all work hours and we added those up and divided by the total, we're 90% confident that the average for all the nurses would be between these two numbers. So now we'll look at two examples of, if we're provided with the data, how we can find the information that we necessary to construct the confidence interval. Unhealthy days in cities is what the data is about. So the number of unhealthy days based on the AQI air quality index for a random sample of metropolitan areas is shown. Construct a 98% confidence interval based on the data. So we know with our confidence interval, we need to know the sample size. That we can find just by counting it, right? There's 10 values here. 4, 5, 6, 7, 8, 9, 10. So that's not given to me. The other things not given to us is the sample mean. So since this is sample data, we can calculate the average, add those up, divide by 10. So 33.5 days would be the average number of unhealthy days for this sample of metropolitan areas. Now, to find the standard deviation, we have a formula that comes from a while ago. So if we recall this shortcut formula from chapter 3, when we looked at measures of variation, this is what we could use to find the standard deviation. You can also use technology if you know how to find it in the calculator or in Excel still. You can do that as well. But I just wanted to kind of review this because the process wasn't really too difficult, maybe a little bit tedious, but you'd only have to do it 2 or 3 times in your homework if you chose to do this by hand. So the sum of x, we already know that, is 335. The sum of the squareds of x, we have to do 61 squared and 12 squared and 6 squared all the way to this 40 squared and add those together. And then we can set up the formula quite easily. And so we get the standard deviation is 27.68 days. So that is quite high standard deviation, but we should have expected it to be high due to the variability in the data. The fewest number of unhealthy days was 5, and the most is 93. So it has a pretty wide spread. So this is like the typical spread from each value compared to the mean. And so now that we've found those two values, we can utilize find our critical value based on the fact that we want to construct a 95% confidence interval. So still we need degrees of freedom. So 10 minus 1, which is 9. And then our critical value is going to come from our table. So let's look at for 98% confidence. So here's 98% confidence interval and degree of freedom 9. And they line up here, 2.821. And then we can use our formula. So point estimate plus or minus our margin of error. So 33.5 plus or minus our critical value, 2.821 times our standard deviation divided by the square root of 10. And when we calculate that, now this is our margin of error, right? That's a pretty huge margin of error. 24.69 days is what our margin of error represents. So we have an average of 33.5 days, and we're subtracting and adding 24.69 days to that number. So that's going to create an interval of a 98% confidence for us that we are capturing the true mean number of unhealthy days for these metropolitan areas. So we look at the true mean, which is mu, right? That's the population average, is somewhere anywhere from 8.8 to 58.2 unhealthy days for, let's say, all metropolitan areas. And then we can make our little statement like we did before, so that still has not changed. We are 98% confident the true mean number of unhealthy air days for metropolitan areas is between 8.8 and 58.2 days. So more or less the process is very similar to what we looked at before, and we'll do one more example of how to find and interpret a confidence interval when we don't know the standard deviation. So the number of calories per candy bar for a random sample of standard size candy bars is shown below. Estimate the mean number of calories per candy bar with 98% confidence. So we already know that we need to find the sample size. That's just by counting the data set. There's 14 values there. We need to find the sample mean. So if you add up all those numbers, 3405 divided by 14, so 243.21 calories. This value does have meaning. And then we want to find our sample standard deviation. So to find the sample standard deviation, we use our shortcut formula from chapter 3, and we get 23.82 calories, which this number is not as high compared to the, even though they both were in the 20s, these values are 3-digit values versus the other ones. Those were all 2-digit values, and there were a lot of values below the standard deviation. So you can kind of, this is not that high compared to the other value. And then our 98% confidence interval, of course, based on degrees of freedom. So 14 minus 1, which is 13. We consult our table. So 13 degrees of freedom, and we want 98%. So we are looking at 2.650 is our critical value that we'll use for this. And then we do our confidence interval formula. point estimate plus or minus critical value times standard deviation divided by the square root of the sample size. And then we have our point estimate plus or minus our margin of error. So this is 16.87 calories that we're subtracting from the average calorie of the sample, and that we're adding to the average calorie of the sample to construct our interval. So 22.6.34 through 260.08. That's what we're estimating the true mean calories per candy bar based on the sample data collected. And then of course we interpret that. We are 98% confident that the true mean number of calories per candy bar is between 226 and 260 calories. And so that's more or less, hopefully, after seeing the process for both videos, you feel as though it's a very similar process. Just one confidence interval uses table E for the standard normal distribution because we know the value of sigma, and the other confidence interval process uses table F for the t distribution because we don't know what sigma is. So that's the main difference there, being able to discern between when am I going to use table E versus when am I going to use table F. And that same process will be carried over into chapter 8. So look forward to that.